Ever wish you could, like, weigh something as a massive as a whole cluster of galaxies?
Oh, yeah.
Well, that's what today's deep dive is all about. We're looking at how scientists are doing just that.
Wow.
This research paper combines observations from two powerful telescopes,
Okay.
the South Pole Telescope
Good.
and the Dark Energy Survey,
Right.
and they're using them to measure the mass of galaxy clusters
Okay.
in a pretty mind-boggling way. They're using the light from the Big Bang itself.
Yeah, it's pretty remarkable. They're using a phenomenon called CMB lensing, where,
CMB lensing.
yeah, where the gravity of these massive galaxy clusters
Mm.
actually bends the path of light from the cosmic microwave background, or CMB for short, as it travels towards us.
So the CMB is like a giant cosmic backdrop,
Mm.
and the galaxy clusters are like warping it.
Exactly. Just imagine looking at a distant streetlight through a warped window.
Okay.
The light gets distorted. Right?
Yeah.
Well, by carefully measuring these tiny distortions in the CMB, scientists can actually infer the mass of the galaxy cluster causing the bending.
That's incredible. But
Mhm.
why are we so focused on figuring out how much galaxy clusters weigh? I mean, aren't they just, well, a bunch of galaxies hanging out together?
Well, they're much more than that. Galaxy clusters are the universe's heavyweights. They're the largest structures held together by gravity,
Mm.
and they hold clues about some of the biggest mysteries in cosmology,
Okay.
like dark energy
Right.
and dark matter. To unlock those secrets, we need to know their mass.
So it's like knowing the weight of a cake can tell you about the ingredients and how it was baked.
That's a great analogy. And just like a baker needs a reliable scale,
Right.
cosmologists need accurate ways to, weigh these galaxy clusters.
Okay, let's unpack that.
Yeah.
Paper mentions something called a mass calibration problem.
Uh-huh.
What makes it so tricky to get an accurate measurement?
Well, we can't just put a galaxy cluster on a scale.
Uh-huh. Right.
So scientists rely on indirect methods, okay, and each has its own challenges.
I see.
This paper focuses on two main methods: optical weak lensing
Okay.
and CMB lensing.
Right.
Optical weak lensing looks at how the cluster's gravity distorts light from distant galaxies, kind of like a funhouse mirror effect.
Okay.
CMB lensing, as we discussed, uses the distortions in the light from the Big Bang.
So this study uses the CMB, the oldest light in the universe,
Yeah.
to weigh something that formed billions of years later. That's pretty mind-blowing.
It really highlights the interconnectedness of the universe, I think. This study, in particular, combined the strengths of the South Pole Telescope, which observes the CMB,
Okay.
and the Dark Energy Survey, which maps out the distribution of galaxies and clusters.
A powerful duo. What did they actually find? Did they manage to weigh these galaxy clusters?
They did. They analyzed 3 different samples of galaxy clusters, each with a different way of selecting clusters to study.
Hmm.
Think of it like trying different lenses to get the clearest view of those distorted images.
And by analyzing these distortions, they could determine the mass of the clusters.
Precisely. And they were incredibly careful to account for possible errors. Measuring those faint distortions is like trying to hear a whisper in a hurricane.
Wow.
I mean, there are other things out there that can create similar distortions in the CMB.
So it's not just a matter of pointing the telescope and seeing the distortions. There's a lot of analysis and filtering involved. What kind of things did they have to account for?
One example is something called the thermal Sonia-Zeldovich effect, or TSZ for short.
Yeah.
It's a distortion caused by hot gas in the galaxy clusters interacting with the CMB. To isolate the lensing signal,
Right.
they had to remove the TSE effect,
Okay.
other contaminating signals.
That sounds complicated. How did they manage to filter out all that extra noise?
Well, they developed a very clever technique. Imagine taking multiple blurry pictures of something,
Okay.
each slightly offset, and then stacking them together.
Like those trick birthday candles that relight themselves?
Yes, exactly.
Huh.
By carefully aligning and stacking images of galaxy clusters, they could amplify that faint lensing signal and make it much easier to measure.
Oh, I see.
They also used a weighting system to give more emphasis to clusters with stronger lensing signals, further refining their measurements.
So they're basically boosting the signal and filtering out the noise to get the most accurate measurements possible. And they did all this for 3 different samples of galaxy clusters.
Exactly. They wanted to see how their mass measurements might vary depending on the types of clusters they were looking at.
Makes sense.
And what's amazing is that for each sample, they managed to measure the average mass of the clusters with incredible precision.
Okay, on the edge of my seat, what were the results?
They found that the average masses of the 3 cluster samples were incredibly consistent,
Uh,
demonstrating the power and accuracy of their methods. And these are some of the most precise CMB lensing measurements to date.
that's impressive, but I'm guessing it doesn't stop there. This is just one piece of a much larger puzzle, right?
You're absolutely right. This research is just the beginning. It's paving the way for even more precise measurements in the future, with new telescopes like the Simons Observatory and CMBS-4 coming online.
So we're talking about an even clearer view of those distorted images
Yes.
and even more accurate mass estimates. This is where it gets really interesting.
Indeed. And with that level of precision, CMB lensing becomes an incredibly powerful tool for exploring the universe's biggest mysteries.
All right, I'm hooked. Tell me more about what this means for our understanding of the universe, and especially those mysteries like dark energy and dark matter.
Imagine trying to understand a recipe, but you can only look at like the final baked dish. You might be able to guess some ingredients,
Yeah.
but you wouldn't know the exact amounts.
Right, and you would know like the steps the baker took.
Exactly. And that's kind of the challenge cosmologists face
Okay.
when studying the universe.
Yeah.
We could observe the final product, the galaxies, the clusters,
Right.
the large-scale structures, but we need to figure out the recipe, the underlying physics that created it all.
And that's where accurately measuring the mass of galaxy clusters comes in.
Precisely. Knowing their mass helps us understand the role of dark matter.
Okay.
That mysterious stuff that makes up most of the universe's matter,
Right.
but doesn't interact with light.
Right.
It also helps us study dark energy,
Yeah.
that even more mysterious force that's driving the universe's accelerated expansion.
So it's not just about the clusters themselves, it's about using them as a tool to investigate
Yeah.
those bigger cosmological mysteries.
Exactly. It's like those clusters are cosmic laboratories giving us insights into the fundamental nature of the universe.
Okay, I'm starting to see the bigger picture here, but let's zoom back in on the paper itself.
Okay.
They go into quite a bit of detail about their methods.
Yeah.
There's this whole section on their lensing estimator.
Right. The lensing estimator is essentially a mathematical tool that they use
Okay.
to extract the lensing signal from the CMB data.
I-
Think of it like a detective's magnifying glass,
Right.
helping them to pick out the tiny clues hidden within a complex crime scene.
So it's not just about seeing those distortions in the CMB. They need this special tool
Yeah.
to analyze them and extract meaningful information.
Exactly. They also take into account the fact that different clusters
Right.
will cause different amounts of lensing, depending on their mass and how far away they are.
I see.
They use something called richness bins to group clusters together
Okay.
based on how many galaxies they contain.
Okay.
It's like sorting apples by size, small, medium, large.
Okay, I'm picturing these groups of clusters, each causing a different level of distortion in the CMB.
Uh-huh.
But they also mentioned redshift bins. What are those all about?
Redshift is a way of measuring how far away an object is in space.
Okay.
By dividing the clusters into redshift bins, they can analyze groups of clusters at different distances from Earth.
Okay.
It's like looking at the universe at different points in its history.
That's pretty cool. So by looking at clusters at different distances, they can study how the universe has evolved over time.
Exactly. And they compared their mass measurements
Right.
to those obtained using a different method, optical weak lensing.
Right. We talked about that earlier. It uses the distortions in light from distant galaxies, not the CMB, to estimate cluster mass.
And the exciting thing is that their CMB lensing measurements agreed really well
Okay.
with the optical weak lensing results across a range of cluster types and distances.
So it's like having two independent witnesses corroborating the same story.
Exactly. That agreement gives us a lot of confidence in both methods
Right.
and strengthens the case for CMB lensing
Yeah.
as a powerful tool for cosmology.
So we've got these two powerful methods, optical weak lensing and CMB lensing,
Yeah.
each with its own strengths and weaknesses. It sounds like combining them is the key to getting the most accurate and reliable measurement.
Absolutely. It's
Yeah.
like having two different sets of eyes on the universe,
Yeah.
giving us a more complete and nuanced understanding of what we're seeing.
Okay. All of this is fascinating, but I'm still trying to wrap my head around the technical details.
Yeah.
The paper mentions something called a TSZ nulled mat.
Yeah.
What on earth is that?
Remember we talked about the Thermo-Sunyaev-Zildovich effect?
Yes.
Or TSE, that distortion caused by hot gas in galaxy clusters?
Yeah, the one that makes it harder to measure the lensing signal.
Exactly. Well, a TSE nulled map is a special kind of CMB map
Okay.
where they've used clever techniques to essentially subtract out the TSZ effect, leaving a much cleaner signal.
So it's like using noise-canceling headphones to block out all the unwanted sounds so you can hear the music more clearly.
That's a perfect analogy.
Yeah.
By using this TSZ nulled map,
Okay.
they can more accurately measure those tiny distortions caused by the lensing effect.
That makes a lot more sense now. But even with all this careful filtering and analysis, there must still be some uncertainty in their measurements, right?
Of course. Every measurement has some level of uncertainty.
Right.
But that's where the beauty of science comes in.
Okay.
The researchers in this paper are incredibly transparent about their methods and the potential sources of error. They went to great lengths to quantify those uncertainties and make sure their results are as robust as possible.
That's reassuring. It sounds like they're not just trying to get the right answer. They're trying to understand the limitations of their methods and be as transparent as possible about their findings.
Exactly. They also compared their measurements to theoretical models and simulations to make sure everything lined up.
Right.
They ran their analysis pipeline on simulated data to make sure they could recover the true mass of the simulated clusters, even with all that cosmic noise added in.
So it's like a stress test for their methods, making sure they can handle the messiest of cosmic data.
Exactly. They really left no stone unturned in their quest for accuracy and precision. And the fact that their results hold up so well under scrutiny is a testament to the rigor of their work.
Okay, I'm feeling much more confident in their findings now.
Okay.
So they've weighed these galaxy clusters, they've compared their results to other methods, and they've accounted for all sorts of potential sources of error. What's the next step?
Well, this research is just the tip of the iceberg. They talk about how future telescopes, like the Simons Observatory and CMBS-4, will revolutionize this field. These telescopes will be even more sensitive, allowing us to detect even fainter distortions and study even more distant galaxy clusters.
So we're talking about an even clearer picture of the universe and an even deeper understanding of its mysteries. This is where I wish we had a crystal ball.
It's certainly an exciting time to be studying the universe. Imagine the possibilities.
It's like we've been using a blurry old map to navigate the universe, and now we're getting our hands on like a high-definition GPS.
That's a great way to put it with these new telescopes. We're going to have an unprecedented view of the cosmos.
Right.
And that means we can start to answer some really big questions about how the universe evolved and what its fate might be.
Okay, so we've talked about the weighing galaxy clusters with incredible precision. But what about the so what? Why should we care about these incredibly massive objects billions of light years away?
Well, what's fascinating here is that these galaxy clusters are like giant signposts pointing us towards a deeper understanding of the universe's fundamental ingredients. Dark matter and dark energy.
Right, those cosmic mysteries we keep circling back to remind me again why those are so important to cosmologists.
Think of it this way. Dark matter acts like the scaffolding of the universe, providing the gravitational pull that allows galaxies and clusters to form. Without it, the universe would look very different.
Right.
Perhaps without any galaxies at all.
So it's like the invisible glue holding everything together.
Exactly. And then we have dark energy, which is even more mysterious.
Right.
It's this force that's causing the universe to expand at an accelerating rate, like a cosmic accelerator pedal.
And by studying these massive galaxy clusters, we can learn more about both dark matter and dark energy. How does that work?
The more accurately we can measure the mass of galaxy clusters, the better we can understand how much dark matter they contain and how it's distributed. This helps us refine our models of how dark matter interacts with normal matter and how it shapes the universe on the largest scales.
So it's like using those cluster masses as clues to map out the invisible dark matter scaffolding.
Precisely. And by observing how clusters evolve over time, particularly how they clump together or spread apart, we can learn about the influence of dark energy and its effect on the expansion of the universe.
So it's a 2-for-1 deal. By studying these galaxy clusters, we're getting insights into both dark matter and dark energy, two of the biggest mysteries in cosmology.
Exactly. And with these new telescopes and techniques, we're on the verge of some truly groundbreaking discoveries. The paper even talks about achieving mass constraints of less than 6% with future observations.
Wow, that's amazing. But I'm curious, are there any other applications for the CMB lensing technique besides weighing galaxy clusters? Could we use it to study other objects or phenomena in the universe?
That's a great question. CMB lensing is a versatile tool.
Okay.
It can help us study the distribution of matter
Mm.
on the largest scales, giving us a glimpse into the very fabric of the cosmos. We can use it to map out those giant cosmic filaments
Yeah.
and voids that make up the large-scale structure of the universe.
So we're not just talking about individual galaxy clusters anymore. We're talking about mapping the universe's cosmic web.
Exactly. And by understanding how that web formed and evolved,
Right.
we can learn about the conditions in the very early universe just moments after the Big Bang.
It's like using this ancient light as a time machine to peer back into the universe's infancy.
This raises an important question for you to ponder. If we can use this light from the Big Bang to weigh galaxy clusters, map out the universe's largest structures, and even peer back into the universe's earliest moments, what other secrets might those ancient photons hold? What other mysteries are just waiting to be uncovered?
I guess we'll have to wait and see. But one thing's for sure, this deep dive has definitely left me with a sense of awe and wonder about the vastness and complexity of the universe,
Yeah.
and a whole lot more questions. Thanks for taking me on this journey.
My pleasure.